In this video, we will learn how to design a communication network in an intelligent swarm system, where all the agents can contact every other agent without the need of ground station. This video is for those who have interest in artificially intelligent swarm systems and wanted to design its communication methods. So consider this as a bigger picture, where there is a one ground station, or we call as the UGV, and then there are 6 other agents spread across in the 3 dimensions. So in all the cases, we have shown these blue lines as the communication between all the agents. So let's say suppose this is agent 1 needs to contact with agent 3, we have this line, and then we have agent 1 contacting with agent 2, we have this line, and so on. So this is how we want to approach the design of the system. We also call this as a mobile ad hoc network design, or MANET, where all the agents can move are mobile and can move all across the 3-dimension space or wherever they want to go. So that's the reason why they are called as mobile. Ad hoc implies that they're instant connection and instant position networking. All right, we're gonna proceed with this picture as our basic design methodology and basic picture to design a communication. So here we want to clear out what is a peer-to-peer network is, so which is also known as P2P. So consider 2 agents named as agent 1 and agent 5. So what we say is a peer-to-peer network is that the data given from 1 is received by 5 at the same time. The 5 data from 5 is also received by 1. So both the actions are occurring simultaneously in the same time frame. So basically it's a duplex methodology of communication, where data is also data is sent to the other agent while data is also received from the other agent, and so there is more bandwidth, more faster data communication between both of them. So that's why we mentioned here the peer-to-peer network can be an ad hoc connection, a couple of computers connected via a universal bus or wireless to transfer files. Each agent can act as a client as well as a server. So here we mentioned that each agent can serve the network and can also act as a client. So here we gonna mention one more thing, that each of the hardware on each of the different agent can receive communication from a single node and can send the data to many nodes at the same time. So for designing such a system, we have requirements as follows. We require a Wi-Fi network with soft APN station capabilities. The AP implies first access point, where one node or one agent can act as a server to many other agents. And it also has the routing capabilities to different agents, and it can transfer data from one agent to the other. So how do we achieve that? We need any board based on ESP8266 chip, but memory greater than or equal to 4 MB, because of the fact that the greater the memory, the faster the data transfer and buffering in the system. Also, the greater the memory, the better we can have a firmware installed into the chip. And what goals does it fulfill? It gives you a secure network because of the Wi-Fi chip. The Wi-Fi chip has different standards as AES, Advanced Encryption Standard, and it has faster data rates up to 72.2 megabits per second. To route the data to different AP or different access points or different clients, we require a Wi-Fi router, which serves the goals to connect the ground to all nodes. It gives a faster processing and data speeds. It should be cheap and fulfills the purpose. And to connect all the communication between the battery or any of the microcontroller with your Wi-Fi module, we require jumper cables. And for that, for the connections, so here we define the peer-to-peer network, or P2P, more in detail. We define this as in dramatic form between agents. So we're defining data and acknowledgement blocks. So here we have this, let's consider as sender and receiver. We have one side as a sender and the other side as a receiver. What we do is, in sender mode, we give the data as follows. We declare two blocks as sender and receiver, and here you can see that this is sending and receiving. Okay, is this one. This is green is for sending and red will be for receiving. Okay, the sending end is defined over here and the receiving end is defined there. Since it's a P2P network, both will have the sending end and a receiving end. Okay, so first we have data block from the sending end, and we have acknowledgement, which is basically saying that okay, this is a data packet received, and to give as that in order to receiver to tell to the sender that data has been received, it sends an acknowledgement packet after every data packet it receives. So in the sending end, we could have location. Since it's a swarm system, any swarm system, maybe a drone swarm system or a nautical swarm system or any other ground-based swarm system, we need to have a location of the different agents, and we need information about those agents or any information that agent could carry. Okay, we can also have any command into that agent, which usually is from ground station or the ground control station, and we have the location of the receiver on the sending end and information acknowledgement also as a command acknowledgement. So let's say suppose we want to send location to the receiving end. We send the sending end of the sender sends location to the receiving end. The location of the receiver as acknowledgement is sent back to the receiving end. So here what we have done is we have modified our acknowledgement packet. What we are saying is that the acknowledgement packet is basically the location of the receiver or any other different node. So the location of the node or agent is being acted as an acknowledgement packet. So any information about the of the location is equivalent to the acknowledgement packet. So we send the information to the receiving end, and at the same time we receive the information acknowledgement to the receiving end of the sender. Then we have the command from the sending end, and then we have the command acknowledgement from the receiving end, from the sending end of the receiver. Okay, so for a while we need to drop this thing the other things, and we want to discuss more about the location. What is the location here? So what we do is location. Why is it important? Why do we actually put location as an acknowledgement packet? So for that, we see that what the location tell us and what purpose does it add to the system, and why we are changing the acknowledgement packet as a location. So it tells the coordinates of the node in 3D space, and this will help in guidance and navigation of all the drone systems or maybe all the swarm systems. And it tells how far the node is from one another and in what orientation, because of the sensors, because of the sensor of the data on the system itself. So let's suppose the sensor is taking up position coordinates, and it's also magnetometer is also telling in which direction or which north direction or south direction is facing into, and the barometer will be giving its height. So based on all those three inputs, we can detect what is the current position or direction of each of the individual agents. And it adds facilitates the communication team to choose how to transfer the data to a particular node via hopping the network. So how do we hop the network? We'll discuss that later. But basically it tells us how and how we'll be designing our hopping algorithm and how do we hop the data over to the network. Okay, and it also explains how the cluster as a whole is behaving and information about the proximities of different nodes to one another. This will help the task control to implement the strategy and help GNC to, or basically guidance, navigation and control, to implement clustering algorithms. So for any swarm system, we all know that there is a one task control algorithm or task control team which has to design how the whole of the swarm behaves as a total. So for that only we design the task control algorithms. Okay, so another importance, the way of motion help in calculation of the speed and velocity. So we also know that how each of the nodes and each of nodes, or maybe known as agents, are behaving in 3D space. And that will help task control to know which waypoint has been crossed at what second and or what time. Okay, so in all, location seems to be very important. Also, okay, the questions to address: how the node is located, or how is the communication channel working or will work? What kind of communication method or protocol will we use? What are acknowledgement packets and how do they work? What does acknowledgement or any packet contains? How are we eventually designing the managed mobile ad-hoc network? What is the range of the system and how do we calculate it? What happens in different scenarios where nodes may fail? What happens? What are the risks present in the system as a whole? What happens if guidance, navigation, and control system fails? How will the connections still work? So we'll address all the questions one by one. So let's start with the acknowledgement packets. So basically, acknowledgement packets are ACK packets are acknowledgement packets that are used to tell the receiver that the data package has been received. Okay, here the physical layer uses its own acknowledgement packets, and it is a hardware thing. We cannot change it. But if you think about the data link layer, the packet delivery system could be modified in accordance to our needs. We use a hybrid OSI model, well known as Mavlink protocol. We basically are combining both of the Mavlink and an OSI model into another fuse model, which we don't have a name though, but we use it. Okay, the data link layer provides node-to-node transfer and medium access layers to work on IEEE 802.11, which is basically the Wi-Fi standard. Okay, and the node-to-node transfer in Mavlink is quite simple, but we modify the acknowledgement packet. Okay. The modification of the acknowledgement packet is as follows. We use a location of the node and its distinct assigned identification as the acknowledgement packet. We reduce the usage of extra bandwidth required for different acknowledgement packet along with location. So basically what we have done is instead of giving an acknowledgement packet along with the location as a complete bigger packet, we have modified the acknowledgement packet as a location packet itself. So in all of the system, in all of the system, all the agents and all the drones are exchanging acknowledgement with one another as in terms of location, or maybe disguised as location. Okay, also the location is always shared over the channel, and so requirement of a request to know the location of the node is not required. Basically, I don't need to ask any agent from what position is it on and where it is transferring its new coordinates to, and where is it going, or what waypoint has been covered. All of that data is received as an acknowledgement. This is basic key element of our managed development. Okay, so acknowledgement in action. Here we kind of show you in a way of what you call an animated way. So here we have one sender, and there we have one receiver, and here's our acknowledgement packet. In normal conditions, the acknowledgement is moving as follows. It's always shared over to the channel. And now if sender wants to send something to the receiver, what it does is it sends TX. TX is a transfer packet along with the acknowledgement packet in order to tell that receiver, hey receiver, I'm going to send you some data. In that case, the ACK along with TX is sent to the receiver. The receiver now sends the ACK back. The first packet is sent to the receiver, and then the ACK is sent back, and then second packet is sent to the receiver. Along with that, ACK is sent back, and then TX is sent, and after that the acknowledgement receives again. Cycle repeats on again. So in this way, with the same as the TX and acknowledgement sent at the same time, we can not only limit the extra usage of the acknowledgement packet, but we can also signal that what times acknowledgement has been sent along with the TX command received. So every time I didn't need to send acknowledgement along with the location, along with telling that okay, I received some data. The same packet is used to tell the sender that okay, the location is sent, and okay, the data is also sent after signaling of one another of receiving of the TX packet. So we want to discuss more about the communication as a random process. I mean, we need to add some mathematics into it. So what we do in this case is that we consider a communication connection trial between two agents, ground to drone or maybe drone to drone. Consider anything, it's not important at the moment. The thing is that let us see the probabilistic criterion of the connections. So let us denote a succession in connection equals 1 and a failure in connection equals 0. So here we assume that both the events are independent of one another. So event of a connection successful is completely independent of the connection unsuccessful. We also consider that this scope of connectivity is only at the physical layer of the network. At each trial, I say I, we have P success equals Px of I equals 1, which is basically equals to P. Let's say some probability, general probability P. And a failure is Px of I equals 0, could be 1 minus P. Okay, so sequence of random variables x1, x2, x3, dot dot dot, or infinitely x of n, who has success as P and failure has 1 minus P, we can say that expectation of x of I is equal to P star P into 1 plus 1 minus P into 0, which is basically P. So the variance of the system can also be seen as B into 1 minus P. So let us say that if we want a joint distribution of x2, x5, x7, to which we represent as the P x2, x5, x7, x2, x5, x7 due to independence. We basically multiply all of them together. Why we are doing this? This is because of the fact that we want to know that if x2 wants to send data to x7 via x5, what is the probability of the communication between x2, x5 and x7, which is very important at this moment to understand. So now this case is exactly same as asking the ground station to contact nodes x7 via hopping data over x2 then x5. That's what I said. So in one may ask, isn't this the case of conditional probability that finds the probability of data connection of x2 with x5 given that the data is already received by x2? So since the connections are independent, the joint distribution is a simple multiplication of the probabilities. And because it doesn't matter, I mean, between the communication of P of x5 or x2, they're not dependent on one another. It's just independent events happening in the time space. Okay, so conditionally also we evaluate just to fulfill someone asking about more of the systems. So we say that P of xy given that x2 has already occurred is equal to P of xy, but P of x5 along with x2 is equal to P of x2 into x5. This says that both events have occurred independently, because if you calculate these all two events, you'll find this as a result. Okay, so the occurrence of x2 is independent of occurrence of x5. So how much this system robust? Okay, well, here we mean that there are infinite hops. Will the system be able to transfer data each time? We are going to ask them questions. This is likely asking that you flip a coin infinite times to get one every time. This feels impractical. Let's see probably answers about it. So this is basically saying that if we increase the number of drones or number of agents into a swarm, what is the probability that the communication or the packet received by the target node will be a successful? So we basically calculate the probability of success with multiple number of hops. So we want to see how many hops can be possible into a system. Okay, so and we also want to question that if we increase the number of hops, what will happen to the system here? Okay, so the condition is as P of xt equals 1 for all t. So we are saying that the probability of communication is a success is basically equals 1. And we are saying that for all values of t, for all values of different cases, we consider it as 1. We want to see the condition to check. Okay, so by this condition that p is less than 1, the probability is always less than 1. We already know that the P of xt equals 1 for all t is less than P of xk equals 1 for all k. Here we say that the probability of occurrence of system t, which is some arbitrary system, will be always less than probability of occurrence of k, which is equal to 1 for all values of k, where k is less than t. So occurrence of k is less than t, where we are saying the number of tests, number of hopping of k is less than the number of hopping in this case. Okay, so we want to let me remove that. Okay, we want to test basically if the number of hops increases, what happens. That's what I'm asking, that's what I'm explaining at the moment. And so we say that P of x of t equals 1, which is equal to P. So communication that is a success, the probability of an event which there is a success is equal to P, which is less than 1, which is important because it will never be equal to 1. So due to independence, the inequality condenses as P of p to the power t less than P of k. Since number of multiple hops since we consider it as a probability of all the communication between the probability of occurrence of success between all the system to be P, then since being all the system being independent, the total probability of multiple hops with t number of hops will be P of t, which will be very less than P of k for t greater than equal to k. Okay, so for t greater than equal to k, we have this condition. Since the value of p is less than 1, so multiplying it many times rather reduce the value of the probability. Okay, so if k tends to infinity, P of k tends to 0, which concludes that for infinite number of tries, the system will not always work. So the lesser number of hops, the more probability of communication of sending and receiving. Okay, the condition of sender and receiver. So that's what we have concluded here. So if k tends to infinity implies the number grows very large, the possibility of communication will lose. Okay, because of the multiplication and because of the independence of the probabilities between all the agents as a success. Okay, so is the communication process really memoryless? We're going to consider the communication as a process at this moment, and we're going to discuss about this characteristics as a process. Okay, so by saying that, we imply that what happened in the past will not affect in the future. So does this mean that the node or drone already invisible to the ground node going farther may appear suddenly? So we are asking ourselves that, let's say suppose if we have a complete swarm system where one drone is invisible to the ground station and ground station wants to send some data to that invisible node. So it's the condition is that it is going farther away from the ground station. So what is the probability that it will appear over to the grid and to the ground station? Okay, well, actually it's no, it will not happen. Okay, why is that so? We'll explain later. And we're going to consider this statement. Or does it mean that the system knows that the node is going farther away? Also is another question to answer. Since we don't know that the system is going farther because the system is not visible to us, so we cannot give any other condition about the system. Okay, so how do we test it in probability? We consider the system capability. So we ask ourselves the question, so what exactly does the system know? The system is independent to decide on previous positions of the node while contacting them for communication. However, this should be untrue for the task control. So it has contact as in scenario 1 where the systems need to contact an invisible node farther away with a single hop. We'll explain that later. The system chooses the average values of the position or the GPS coordinates each time if any node is invisible. This process, by virtue of its method, is independent of trajectories of the nodes. It just sees the farthest nodes near GPS location and directly contacts it to transfer the message to the invisible node. Hence, choosing of the node in particular range of coordinates is completely independent of the last connection, so is then the system memoryless and independent. However, you could choose the data by task control, position control, but that increases more complexity in the system. That complexity window should only be the task control team and not communication. Also, the maximum distance we use is up to 145 meters. So we believe that this simple, less complex method would be way better than in communication. So for our system, which I designed, we needed the maximum range of 145 meters. But then this system can also work for about 1 kilometers or maybe 2 kilometers and can be expanded up to 7 kilometers if the number of hopping and the communication protocol between them is on Wi-Fi systems only. So we want to answer some of the other questions. The system can also know that in a given amount of time, how many jobs arrived, or conversely, for a given number of jobs, how much time did it take to arrive. So basically, we are trying to see that how much time does it take for one task given to every other node. How much time does it take to the node to receive it and implement it and then send that data back to the ground station. Okay, so that whole system we want to know about. Okay, so the number of successes in n time slots is basically a binomial distribution. So P s equals k is basically, this is a binomial distribution notation. n of k, p of k, 1 minus p, n minus k, where k is equal to 1, 0, 1, 2, 3, n. And this is the expectation, which is np. The variance is np into 1 minus p. Okay. So here we fix time and ask how many arrivals. Here time is discrete, so let us fix the number of arrivals and ask how much time they took. Let's start with the first time until first arrival. Okay, so let's say suppose there are so many events where this is this for the time first arrival, this is all zeros. I mean, at this point, this point, this point, this point, we didn't receive anything. At this time instant, we received something. Okay, so this is, say, let's say t1. This is the total time from not receiving till received. Okay. So we ask what is the probability of the distribution of t1. What kind of random variable is it? So it is p t1 equals t, which is basically an arbitrary value, t, which should be equal to 1 minus p, which is the probability of failure to the power t minus 1 times p, which is the probability of success. So we are saying, if you see in the previous one, which we will say that all the probabilities of failures multiplied by the probability of success, where p is the number of failures and p is the success. Okay. So expectation of e of t1 is equal to 1 by p. Okay, which is a general case. If you have known probability of steady probability in more detail, you know about this, which implies that the lesser the probability, the more the expectations, which is quite evident. We expect connectivity at farther distances, though we know that the probability of connection is low. Okay. And so this is a geometric distribution. We conclude that this system is a geometric distribution. Oh, sorry, I need to underline that one. Is a geometric distribution. Now we can take these observations at different distances during testing, and we will average out all the observations to predict the probability of arrival at those distances. So for example, the probability of arrival at distance 0.1 kilometer is 0.1 kilometers north, 0.1 kilometers northeast, plus 0.1 kilometers northwest, plus 1 kilometers northwest upon 4. This is, we are saying that what is the probability of arrival at distance 0.1 kilometers. So basically we are averaging it out to have to have a value which we give as a threshold to the system. So let's say suppose if this is basically a test method. Okay, so we are averaging out basic different distances to average out the distance between, to average out the communication time between one job sent and one job received in the different case scenarios. So so the more number of testing, the better will be the approximation. So as we know that we can basically extrapolate the averaging methods. So the picture in 2D looks like this. I'm going to explain more about this. Okay, so let's say suppose there is a ground station, then there is a near field region, then the midfield region, there is a far region. Okay, this type of testing we quoted shall work best only for far region because of the fact that the presence of the probability of connection being lost. The losing of connection in the near field would probably occur due to hardware error or the software decoding, and the distance could be a problem in the far region only. Okay, so now by using the probability distribution, the signal strength at different distances, one could predict that how far in the line of sight the node is. So by using the information of distance plus the imposition of the node by GPS, we can detect the height at which the node is flying. Okay, so let's say suppose there is a ground station. Here we kind of using the communication as a Wi-Fi positioning system. We using it as a second order system, and then we are using this as a second advantage of the communication system. Okay, so here's our flying node, and we have a distance prediction and approximation from signal strength and probability data, and we have the GPS location, so difference between position from GPS, and then we can predict the height, at which height it is being flying. Also, the barometer or the altitude meter of the drone can also give the height. If this is in the case when there is no barometer or altitude meter present in the system. Okay, so thus we can predict the approximate position of the node in the space and where it is going with the help of the data we have, and it can be used for the task control, implementation of strategies, or in what way the whole swarm should behave. We can do all of those systems. all of those methods. And we can also see how the clustering is being done and how the task control algorithm or the clustering algorithm is working into the system in real time. Okay, so hopping, this will be showing the hopping method in more dramatic way. Here we mentioned that I packet contains the information of the sender as well as nodes onto which the packet is hopped. Okay, there's a ground node, there's a hopping node, and then there is a receiver node. So let's say suppose if receiver has to receive something from ground, how do we hop it? How do we hop the data over to the network? So first, we have the TX mode sent to the hopping node, which is saying that, hey, hey, node 6, I want to transfer something. So the moment 6 receives TX, it gives back the acknowledgement, okay? And then it sends a data packet with name as 6.1, which is basically saying that 6 send this data to 1, and then at this moment, the 6 will send acknowledgement to ground and it will send TX to the receiver. Basically, it will say that, hey, 1, I want to send you something. In that case, 1 receives the the TX packet and sends acknowledgement packet 6 to the hopping node. And in that case, 6 receives the acknowledgement. It sends acknowledgement back to the 1 and as well as ground that, hey, I received the position of 1. Here I'm going to connect, and it sends the data to 1 at the same time. 1 receives that data and then sends back acknowledgement 6 saying that, hey, the data in the data I packet had identification that it's coming from ground. I've sent an acknowledgement to you which has to go back to the ground. So now the hopping node has to tell the ground that, okay, the data has been received by 1, and it also has to tell 1 that it has received the acknowledgement packet. So in that case, it says the acknowledgement packet and it says A's acknowledgements ACK 6G to the ground. Okay. So different scenarios of communication between nodes. Here we're going to discuss different cases which may occur into the system. So what we do is that we say that the ground nodes needs to contact all nodes. We say this is the kind of conditions we would need, and any nodes need to contact all nodes. We can differentiate between two different cases. Since we have the ground node being a lot of power and with a lot of communication systems, rather than compared to the flying agents or different clients, we differentiate between ground as well as any other node. So the ground nodes has all nodes are visible. In this case, we say that if any number of nodes are invisible, we define in two cases, where all nodes are visible or if any number of nodes are invisible. And here we define the data is heavy, since the data packet could be heavy, or data is less. Okay. In this case, query, what if the message is received by any node but acknowledgement is not returned back to the sender? In the last example where we were explaining a lot of stuff in dramatic way, we asked this question that if the message is received by the node but acknowledgement is not returned back to the sender, what we do? And the second question to ask is that a node is visible at the time of transmission. A direct message was sent from the ground, but node got invisible in a very short duration and didn't receive it. But after one data cycle, it got visible. Okay, so in this case is that let's say suppose you're standing behind the door and somebody knocks that door, and while you go to open that door, somebody just goes away from that door. And let's say suppose and that person just disappear from that door, it goes away from that door and try to enter from the another part. And while you close that door, since seeing that nobody is there, you close that door, and after a while you receive again another knock. In that case, what do? You kind of consider that person as a ghost? No, you won't do that. You're gonna you're gonna open that door again, and then you're gonna transfer. Then you're gonna talk to that person. So the node used for hopping fails. In the third case is that if the node used for hopping fails. So before answering the query, we first define a data cycle, as we have just introduced the word data cycle in the previous slide. Excuse me. So step 1, TX plus acknowledgement is sent. Okay, the node's in transmission mode. Okay, this is a step 1. This we are defining the data cycle. Step 2, acknowledgement is received from the sender. Step 3, the first data block is sent, sender is transmitting alongside both sender and receiver are accepting acknowledgement from other nodes as well, as access points of the chip are many. Acknowledgement is received from the sender. This is defined as one data cycle. So this whole step from 1 to 4 is assigned as one data cycle. Okay. All this is done for the application layer, since either on OSI or Mavlink, the sender counts up to its send sequence. Since the send sequence count can go up to infinity, the system may lose control over the transmission. To gain control of the system obeys a data cycle concept so as to terminate the connection not early and not too late. The average time shall be tested with the nodes with different distance scenarios and velocity in order to fix the time value of the data cycle in accordance to work. Okay. So here we are saying that the average time we define is that the time that shall be tested. So the time which we were showing as previous, where P of T K dot P of T arrival, which was 1 minus P to the power T into P of 1 minus T. We defined it before. Okay, this is the same condition we're going to test it here. Okay. So let me drop that, clear that up. Okay. So how do we proceed? With our scenario that we just said about, we said the ground node needs to contact all nodes. All nodes are invisible, and any number of nodes are invisible. We first consider this case. If all nodes are visible, then the ground broadcasts a message with different IDs of the nodes. All nodes enter into transmission node. The whole node network is a giant receiver. Okay. The acknowledgement packet is sent back to the ground by each and every node. Okay. Okay. The ground node needs to contact all nodes. So all nodes are invisible if any number of nodes are invisible. If any number of nodes are invisible, then we use a criterion mentioned in the report, which is basically the report which we created for our project file. Okay, the report had the methodology there. Okay, we explain more of that here. First, the ground node recognizes the nearest node in the near region using GPS and probability as explained before. It then updates its location matrix in which the position of the invisible node is present. Then it contacts the farthest node with good signal strength and delivers the message to it to hop on that node and then to reach the destination. The message is then encapsulated with tag ID of the hopper and further encapsulated with the tag ID of the receiver, and it encapsulates the information. This shall be one data block. Okay, this whole shall be one data block. One data block. Okay. The receiver, as explained earlier, responds to the received information with an acknowledgement. At this point, the chip on board of the hopper acts as a soft AP and as a station. This ensures hopping of the packet. Okay. So in other case, we also had that if any node needs to contact all nodes, and first it could be that data is very heavy and data is less. If the data is very heavy, usually that shouldn't be the case, but if there is, then the node sends this data to ground. The ground then sends data as explained before, or conversely, if the ground needs to contact a node with a lot of data, then it chops the data into different blocks and sends to the target node via hopping from the multiple nodes simultaneously. Okay, so it could be that some block is chopped and sent to this node and then to that node and then to this and that and this node. So this could be ground, this could be target, this could be 1, this could be 2, this could be 3, 4, 5. So it can send different data blocks at one time from this end, that end, and this end and that end. This make a collision case at this point on the target, but since we have tag IDs of all the data blocks, so the receiver will be able to assemble all that data blocks into one big giant data. Okay, so the collision problem can be solved in this case. Okay. So if the data is less, then the node broadcasts the message with the ID of the receiver. It may use hopping if necessary by the data encapsulation. So in this case, we haven't defined what is heavy data and what is light data. It basically is subjective to define in this case, okay? So it depends on different cases to cases where the developer has different kinds of chipsets. So in my case, if I'm using my standard, mine can go up to 72.2 megabits per second, or basically uh, 9 megabytes per second. So in that case, data transmission speed is very fast. But then if I want to send 1 gigabits of data, I chop it down into different data blocks, and then I send it to through different nodes with different tag IDs. Okay, so that's how we communicate to the target node if that is invisible and the data is very much. In the case that the data is less, let's say suppose 4 MB, that could directly be sent with the tag ID of the receiver, and we can broadcast it quickly. Okay. So query, what if the message is received by the node, but acknowledgement is not returned back to the sender? We are basically considering all of these queries. In that case, we consider the first case as the ground waits for 5 data cycles to receive the acknowledgement. If the receiving time between that time frame, the received data block, sorry, I missed that part. If received data block between that time frame, the process continues. If not, then ground assumes that the node is invisible. Ground proceeds with the method as explained before. Any number of nodes are invisible. If the location of any node isn't available even after the method above 15 data cycles, ground assumes node to be dead. So it could be that in any of the clients or the client server model, or in any of the nodes, any of the agents is fallen down, may have crashed. Then how do we assume that it has been crashed? So that's how the case we see through the communication. Also, the ground waits for the confirmation from all other nodes as well. So if every other node is saying that, okay, I'm not able to receive that data from this node for a while, for 5 data cycles, that the whole system will say that, hey, this node is dead. Okay. And for the case 2, in this case, if the message is received, then the visibility of the node is confirmed by the ground or node by seeing its visibility, which is the acknowledgement. If the message isn't received, then it becomes case 1 exactly. Okay. Eventually, how the ground node has to send data by hopping over to the network. This is a trade-off. This is the trade-off between the data packet loss and connectivity. Okay. Here we define our trade-off between the networking protocol. Okay. In the third case, if the fallen node's electronics are still working, then the data transfer will complete. However, the location of the node is not changing. The communication network looks for 15 data cycles onto the location of non-moving mode. If the node isn't moving till that time, the network assumes that node as fallen. This node can now act as a beacon to locate other nodes easily, as well as this node now does not do much processing. Therefore, this node can be used for data transfer and a beacon to hop data onto other nodes, since most of the processing power can be used for the data communication rather than its attitude of the drone system, or the attitude of the drone, or attitude of that agent. Okay. If the electronics of the node is damaged, implies that there is no acknowledgement received. As explained before, the sending node waits for 15 data cycles. If no response is given, the sender assumes the node to be dead. Similarly, and eventually, the network shall assume the node to be as dead. So if any other questions about in my whole slideshow or in my whole video, please don't ask me, or just kidding. You can email me on my email address, which was basically in the as a watermark in all of these slides before, here at the back. And my email ID is as u.ahuja@cranfield.ac.uk. All right. Thanks for watching. I'll see you next time.